Hi guys, this is Ms. Freeman. Hopefully this is the first video we've had to do while I'm on maternity leave. And we should be at the start of January as long as everything has gone according to plan. So as we discussed, we're going to be working on gases first, and then we'll talk a little bit about the different types of solids. And then we will move on from there into thermochem, which will hopefully be around March, at which point in time I will hopefully be back with you guys. So let's go ahead and get started. Gases are something we've already talked about and something we should already be fairly familiar with and fairly comfortable with. So just kind of doing some review and then tying in some of the new material you'll need to be able to do with gases and AP chemistry. Okay, so first and foremost, what do we already know about gases? So we should remember the fact that gases have either weak or few intermolecular forces. Remember, we're not trying to use weak or few interchangeably. There is a big difference between those. You have your weak intermolecular forces like your LDFs, and you have your strong intermolecular forces like your dipole-dipole and your hydrogen bonds. You can have something that is hydrogen bonded, such as water, in a gaseous phase. Well, why is it able to be in a gaseous phase? Because we've added enough energy to break those intermolecular forces. So remember, that is an endothermic process, breaking intermolecular forces, and that results in few or less intermolecular forces. Not weaker, just few and far between. What this allows to happen is it allows the gas to be able to expand in their container. It means they are able to, first off, be compressed and also be able to expand or fill a room. They have fluid motion, which goes along with that freedom of not having intermolecular forces holding it together. They have low densities compared to their equivalent liquids and solids. What I mean by that is water vapor has a smaller density than liquid water or solid water. Again, they're compressible. This is, again, due to the fact that there's no intermolecular forces present. So there's space between the molecules, and that allows us to be able to compress them and fill that space. As they are being compressed, keep in mind that some gases may have strong enough intermolecular forces that as you get them close enough, they will start interacting and could very well at that point in time condense or turn back into their liquid phase. And then we also have the word effusion and diffusion. Hopefully we remember those to some extent or another, but just in case we don't. Okay. Effusion is very similar to diffusion in all reality, but there is a slight difference. Both of them are dealing with the spreading out of gases. So effusion is the spreading out of a gas through a tiny pinprick hole in a vacuumed chamber. So in other words, let's say we completely empty out a room of all gases and we put a little pinprick hole into that room. Gas is now able to flow through that hole into that room, and it's naturally going to do that just because of the nature of a gas. And we call that effusion. Diffusion, the same idea, but instead of it being a vacuum, it is just a regular room. So this would be like spraying perfume in one corner of the room and the fact that it spreads and fills the room. Coming back up here to discuss this idea of intermolecular forces, I want us to think back to Coulomb's law real quick. Hopefully remember that, but we have our force equals, this is our force of attraction or repulsion, but in this case we are dealing with attraction with IMFs. Charge 1 times the charge 2 over the radius squared. So just kind of keeping an idea of what's going on here. Why do gases have such weak or few intermolecular forces? It has a lot to do with the fact that they are so spread out, which is going to be our radius. So if I have two molecules that are really close together, this radius will be fairly small. And remember what that's going to do. If I have a small number on my denominator, it makes my force of attraction much larger, therefore stronger or more frequent intermolecular forces, depending on what we're looking at. Versus in a standard gas, like the oxygen and the air, they're much further spread apart. And this distance is going to become large, which gives us a larger denominator, which means our force of attraction will decrease in that case, again, giving them the ability to not have intermolecular forces or have very few spread out intermolecular forces. Now keep in mind, gases are moving freely, so there will be points in time where we have large gaps between them and we have small gaps between them. So there will be some interaction on occasion, and then a lack of interaction at other points in time. It just kind of depends on the amount of gas, the size of their container, as well as their energy, which we'll talk about as we move through this video. Okay. All right, so first and foremost, let's back up and grab some of our terms that we should already know. Pressure, if we remember that from last year, because we did spend a lot of time on gases last year already, pressure is nothing more than the force in a specific area. So as these gases are moving around, they are banging into each other, and they're banging into the walls of the containers. So think literally like having a box, a sealed box, that you open up and you throw a bunch of bouncy balls in here. Well, what are those bouncy balls going to do? Well, they're going to be bouncing around all in here. They're going to be colliding in with each other. They're going to be colliding in with the walls. The force in which they are colliding with the walls is pressure, meaning if I throw a bunch of bouncy balls in, they're going to be colliding with the walls more often, versus if I throw just a few bouncy balls in, they'll be colliding with the walls less often. So we end up with a high pressure in the first scenario, low pressure in the other one. And that's assuming we throw them with the same amount of force. Now let's say I take those few bouncy balls and I throw them with a much higher force. Now they're bouncing around more readily and more frequently. So we could very well end up with a high pressure in either situation. So there are two factors that play a role with pressure. And that is the amount of collisions and the energy of those collisions, and those would all be under this kind of force idea. We have several different ways we measure pressure, if we remember those. We have pascals, which really in chemistry we don't use pascals so much as kilopascals. If we remember that term and remember a kilo, there would be 1,000 pascals and 1 kilopascals, just so we can kind of remember that conversion. We also have millimeters mercury, okay, which just comes from the original barometer where they had mercury in them. And I think I've got a picture on one of the later ones, but just so we can kind of see, remember they would have a bowl of mercury sitting in here, and they would have some type of tube coming out of it. Pressure from the outside would push down on that mercury. It would go up that tube, and they would measure how many millimeters it went up that tube, and that's where the term millimeters mercury comes from. Obviously, we don't use millimeters in America, we use inches, so you may see inches mercury on the weather station for the pressure outside, the barometric pressure. Okay. Really, in chemistry, the common one we use is ATM. That's our standard SI unit for pressure, ATM being atmospheres. Okay. And then we also do have torr, which 1 torr is equal to 1 millimeter mercury. So really, they're the same measurement, just different units. Okay. We also have STP and temperature to review. So remember, STP stands for standard temperature and pressure. This will occur at 0 degrees Celsius and 1 atm. Okay, and 1 atm is equal to 101.3 kilopascals, 14.7 pounds per square inch. If we remember that term, you probably have already seen that term if you're driving and having to fill your tires. You would see PSI, pounds per square inch. That's where that comes from. This is not ever used in AP chemistry, but it is a common form of pressure, especially in America. We have millimeters mercury, which is 760 at 1 atm, and then 760 torr. So again, these two are identical in their measurements. Okay. We also have the idea of what temperature is. So we talked about pressure. Pressure is the amount of force per area of the collisions of the gas molecules. So it's really just how often the gas molecules are colliding with the wall and with what force they're colliding with the wall. What is temperature? Temperature, remember, is the measurement of kinetic energy, but very specifically, it is the measurement of the average kinetic energy. And I am specifically putting an emphasis on this word average. So if we think back, what does the word average mean? Average means not all of them are going to have the same kinetic energy. We very easily in one container could have something at 0 degrees Kelvin, which yes, I know is really more of a theoretical measurement, and this is just kind of theoretically, and we could have something up all the way up at 100 Kelvin, okay, and that average would be somewhere in between them, and that would actually be where our temperature lies. So when we talk about temperature, we do have to recognize that not every molecule will be moving at the same kinetic energy. It's an average of those kinetic energies. Also keep in mind, when we refer to kinetic energy, we are actually talking about, well, not speed. I'm about to write speed on here. We are really talking about velocity, which I can't spell. There we go. It's referring to the velocity of the molecule. So really it comes down to their motion of those molecules. Okay? And remember, in gases, we don't ever really use Celsius. We use Kelvin. And remember, our conversion between Celsius and Kelvin, we would have whatever our degrees Celsius plus 273 equals Kelvin. And I believe that is on your conversion sheet. So it's not something you have to remember, but don't forget that anytime we do anything with gases, we do need to convert to Kelvin to be able to do the math appropriately. And the reason we do convert to Kelvin is because you can't have negative pressure. So if I'm at negative 25 degrees Celsius, when I do my math with this number, I would end up with a negative pressure or a negative volume. That can't happen. So we have to convert it into a positive number, and because there's nothing below 0 degrees Kelvin, we convert it into Kelvin, so we keep everything positive. Okay, let's keep talking about this. So we just talked about this average kinetic energy. Okay, average kinetic energy, if you're in physics, hopefully we've already seen this equation, but you may not have. Average kinetic energy is equal to 1/2 mass times velocity squared. What does that actually mean? That means that as mass increases, okay, we would increase our kinetic energy. As mass, or as volume, or velocity, not volume, excuse me, if velocity increases, we would increase our kinetic energy, and vice versa. If we were decreasing mass, it would decrease kinetic energy. If we were decreasing velocity, it would decrease kinetic energy. Now, in a lot of what we do in AP Chemistry is not so much using this equation. You'll notice this equation is not on your formula sheet in any way, shape, or form. What do we do with this? We use this to compare two different gas molecules. So let's say I'm looking at hydrogen and I'm looking at water, and we're going to assume both of these are gases. And what we do is we say, okay, they're both at 25 degrees Celsius. Well, what does that mean if they're both at 25 degrees Celsius? That means they are both at the same temperature, and therefore they have the same kinetic energy. And if they have the same kinetic energy, that means they can't have the same mass and velocity, or they can't have the same velocity because their masses are different. So if we think about it this way, we would have the kinetic energy of hydrogen is equal to the kinetic energy of H2O. So what does that mean? That means the mass of H2O is much higher, and the mass of hydrogen is much lower. Okay? If these two have to equal the same number, that means what's changing is our velocity. If I decrease my mass to get the same kinetic energy, I have to increase my velocity, and vice versa. If I increase my mass, I have to decrease my velocity. So what does that actually mean in terms of these two gases? It means hydrogen will be moving much faster, okay, whereas water would be moving much slower in comparison. And that's again because if they're at the same temperature, they have the same kinetic energy. So think about it this way. You would have 1/2 mass times velocity squared equals 1/2 times mass times velocity squared, where hydrogen's mass is much smaller and water's mass is much larger. So that means velocity must be faster for hydrogen, and for water it must be lower so that these two numbers can actually equal each other. Okay, and that's a very common conception or common concept through AP Chemistry and through some of the problems we're going to be working with. So, for example, check this guy out. What I want you to do, I'm going to stop here for right now, and we'll come back and watch the next video in just a moment. I want you to try answering this question on your own using the concept we just talked about. Now, there is a lot going on in this question, so talk with your neighbor, see what you come up with, and we'll talk about it at the beginning of the next video. Thanks, guys.